Hello, welcome to the Medical Imaging Lecture Series. Today I am going to talk about X-ray imaging system, who invented it, and physics behind generation of X-rays. An X-ray imaging system is a medical imaging setup that uses X-rays to create images of the inside of the body. These systems help doctors diagnose diseases, detect injuries, and guide medical procedures. X-rays are electromagnetic rays. The key components of X-ray system are X-ray tube, high voltage generator, image receptor, control console, and mechanical support system. We can see joints, bones, and soft tissues in an X-ray image. Now let us see the invention story. Wilhelm Röntgen discovered X-rays in 1895. Wilhelm Conrad Röntgen received the first Nobel Prize for Physics in 1901 for his discovery of X-rays. X-rays are electromagnetic rays. They travel like a light at the speed of light. X-rays interact with matter as if they are particles rather than waves. These particles are actually discrete bundles of energy, and each of these bundle of energy is called as quantum or photon. The amount of energy carried by the photon is directly proportional to the frequency. Here Planck's constant is the constant of proportionality. By considering both wave concept and particle concept theory for X-ray, we can conclude that photonic energy is inversely proportional to its wavelength, which is always expressed in angstrom unit A. Now let us see how X-rays are produced. Inside of the X-ray tube, free electrons are created at the cathode filament through the process of thermionic emission. These electrons are accelerated through the X-ray tube by a high voltage that is in kilovolts. Electrons are decelerated when they interact with the tungsten atoms in the anode target, and through this process they create X-rays. There are two processes through which X-rays are produced. 1. Electrons nucleus interaction, which is called as Bremsstrahlung radiations. 2. Electrons interaction, which is called as characteristic radiations. Let us see one by one. Bremsstrahlung radiation is one of the processes through which these X-ray photons are created. So here's how it works. A tungsten atom, like all atoms, has a positively charged nucleus because of the protons, and it's surrounded by negatively charged electrons. All of these charged particles have an electric field that radiates around them in nucleus as a positive electric field, and the electrons have a negative electric field. When electrons from the cathode enter the anode, some electrons are attracted to the positive charge of the nucleus within these atoms. The negatively charged electron is attracted to that positive charge in the nucleus, but when this happens, the electrons slow down or break, and they also change direction, called deflection. This lost energy is released in the form of an X-ray photon. This process has a name. It's actually called Bremsstrahlung radiation. The meaning of Bremsstrahlung is breaking radiations. De Salle. The law of conservation of energy says that energy cannot be created. Hence, when electrons slow down, its kinetic energy is reduced, and this reduced energy is converted into X-ray. The energy of a Bremsstrahlung radiation photon depends on a few factors, one of them being the energy of the incoming electron. If the incoming electron has an energy of 100 keV, maximum energy photon that can be created is 100 keV. Radiation also depends on how close the electron passes to the nucleus. If the electron passes very close, as in this example, it will slow down significantly, change directions completely, and give up most of its energy, creating highest energy photon. If the electron passes a little far from nucleus, the generated X-ray energy is low. Like this process creates the spectrum of low energy to high energy X-rays. A single exposure creates hundreds of millions of X-ray photons, and almost all of these photons are Bremsstrahlung X-rays. The curve is short on the left, because most of the low-energy Bremsstrahlung X-rays have been filtered out of the beam. These low-energy photons came from electrons that slowed down not much at all. They can't penetrate the tissues of the patient, which is where they need to be filtered out. The curve is also slow on their rights, because very few Bremsstrahlung X-rays are created with the high energy. The curve is tallest in the center, because most Bremsstrahlung X-rays are having moderate energy level. Now let us see the phenomenon of characteristic radiation. Each electron in the target atom has a binding energy, Be, that depends on the shell in which it resides, K shell, highest Be, L shell, next highest Be, and so on. When the energy of an electron incident on the target exceeds the binding energy of an electron of a target atom, it is energetically possible for a collisional interaction to eject the electron and ionize the atom. The unfilled shell is energetically unstable, and an outer shell electron with less binding energy will fill the vacancy. As this electron transitions to a lower energy state, the excess energy can be released as a characteristic X-ray photon, with an energy equal to the difference between the binding energies of the electron shells. Binding energies are unique to a given element. The emitted X-rays have discrete energies that are characteristic of that element. Within each shell, other than the K-shell, there are discrete energy subshells, which result in the fine energy splitting of the characteristic X-rays. Characteristic X-rays other than those generated by K-shell transitions are unimportant in diagnostic imaging because they are almost entirely attenuated by the X-ray tube window or added filtration. That's it for today. We will see how X-ray interacts with the matter in the next lecture. Thank you.